Hello, in this episode, we're going to introduce genetic algorithms, and I'll show you how it's being implemented using the frozen game, the simple game we used before. Okay. The genetic algorithm is something that's inspired by the evolution in the biological systems. And there are mainly three things. We'll go in example later, but the three main mechanisms that let me just mention here. The selection mechanism is that we have sort of a certain gene that coded a policy or program that we think is here, and we randomly have many candidates. Like in nature, there are many different kinds of DNAs. We do have it, and the selection is we fit the best ones or the top 10 best ones in terms of some survival scores. So that's the selection process. And then, actually that's a typo. And then we do a crossover. So among the good ones, the strong ones, let's say there are two type of policy or genes that we had. And what do we do is that we kind of mix match sometimes these two. These were the good ones among the many of them. We top, let's say 10 of them, and then we kind of mix them around and see whether the offspring of these mixed around can do better. So this is the crossover. And also once in a while, we just like, if there's one gene here, the policy here, we just randomly switch some of them here, some components here to see if a surprise change will do better. So all this in combination, and then eventually see, do we do this many times, and then to see whether some kind of policies will do better. So let me just get a bit more detail afterwards. So let me go through an example of frozen game. And if you, just to remind you, this is sort of like one of the simplest Atari games, kind of. Princess Elsa plays on a lake, a frozen lake, and had a frisbee, and playing here is the starting position, and drop the frisbee here. So you have to cross the lake. There are parts of the lake, many parts of the lakes are frozen, the F here, which are safe, can move here. But also there are some red, like these holes, where if you step on it, then you'll sink and the game ends, isn't it? So you want to do it. So can you find a safe passage like here to get to the goal and pick up this frisbee? So this is Frozen Lake. It's like a finding the maze game. And of course, we have done it. So there's a couple of suggestive choices of how you can go and safely from start to goal. So, and if you reach the goal, you get 1 point. And the reinforcement learning was kind of the trial and error idea. Choose the action, observe the state, choose the action, you get a reward, and keep playing was the idea, isn't it? And you can tabulate it here like this. And there was this result that we had simulation, and indeed the reinforcement learning did find some passage going to the goal. Okay, so how do we do this in Frozen Lake? So remember there are 16 tiles here, so 16 positions, and there are 4 kinds of actions. As a benchmark, suppose that we just randomly, we have a dice with 4 faces, and we just throw it and randomly do it. So then for all 16 steps here, for all 16 steps, we need to have the policy is that if you're given in a tile, let's say in a state here, what kind of action are you going to choose? That's the policy. So in this case, in the genetic algorithm, we basically have 16 states here, and there are 4 choices of the policies. So how many policies can we possibly have? Well, for each tile, we have 4 choices. The first tile, we have 4 choices. The second tile, we have another 4 choices, the 4 times 4. And then the third tile, we have yet another choice, 4 times 4 times 4. And keep multiplying, you will get a heck ton of many choices. So there are many different combinations to fill the 16 blocks with these 4 possible moves, isn't it? Shall we try all of them? Maybe. But if you have more tiles, it will get very costly and time consuming to do this, isn't it? But let's try and see how random search works out. Okay, so that's one idea. the genetic algorithm idea is that, so we have a policy. So we have 16 tile position and choose an action what you want to do. And this whole 16 number combination is called a policy. It tells you if you're on this block, what action you choose. If you're on this block, what you choose. And it dictates what you have to do, isn't it? So that is a policy. The action choices are 4. How genetic algorithm works out is that you just randomly generate many combinations, and you have like, I don't know, 4 billion something to choose from. So you certainly can choose many random policies. You pick like the top 10 or top 100 of the best ones. You run the policies, you evaluate these policies that you call populations, so many policies, and it will have a score, isn't it? How it's scored in the frozen game, isn't it? Pick the top 10 or top 100 of them. Let's call it elite set. With the elite set, so suppose that the policy 1 and policy 2 are chosen from the elite set. So you have this one and you have this one. The crossover is that you mix, so you take this one, let's say you have this one, okay, you copy it here as a child, the offspring, but you switch some of these policies, the individual in this block, with policy 2, with let's say 50% chance. You flip a coin. If it's head, then keep it. If it's tail, change it to this one. Head, 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 tail, change here. Head, head, tail, head, tail. You see, and you can get a new offspring. This is the crossover method, and you get a new combination that's different from policy 1 and policy 2. But you pick the policy 1 and policy 2 to be super well performing in terms of survival score. So hopefully the offspring, who knows, may also score well, or even better, isn't it? The other thing that you try is mutation, which is you have this offspring here, you got the offspring here, and now you can just keep it most of the time. But you roll the dice, and let's say it has like 100 faces, and with 1% chance, if that comes that particular face, then you switch it to something else, mutation, or 5% chance, you just switch it. So you keep most of them, but sometimes there's a mutation. To keep doing this, it's a general genetic algorithm that you have a population, you evaluate, keep the strong ones. Then among the strong ones, you do the selection and you do selections, and then you do the crossover and mutation, and keep doing and keep doing for a while, and see whether the resulting population converges to a well-surviving one. In nature, it does. We'll see how it does in computer program version of it. So this idea is fairly generic and general. It's used in many places. But one of the applications to use this, other than this kind of game solving, is, for example, sometimes I get the question, you give us this neural network and these have like how many layers and how many nodes. How do you know how to choose these nodes and design this neural network? The answer is sometimes it's the state of the art than the science, and you just try many things and there are combinations that seems to be working well. That's one answer. Another version of it is that you try a genetic algorithm with the choices of this neural network design as a policy, and just have the genetic algorithm tell you which is a good one, right? Another idea to do this is portfolio optimization. Which stock to pick, how much to hold, these are all policies, and you can run a genetic algorithm to do this. So let's see how it's being done in a frozen program. So let's import the library. It's pretty much similar to what we have done before. So here's the frozen environment, which we did before. And here's just running one episode. You have a reward 0, and then however long the episode you're gonna run, let's say have 100 steps, that used to be long enough. The policy, so if you have, let's say the observation 0, you're at tile 0, this is your state. And then if you're at tile 0, the policy will tell you what action to choose, isn't it? There was a 16 digits, and for each digit, there was a choice of action. So for tile 0, you pick an action. Based on that state and action, you get a next state, reward, and done, and you keep playing it. So this is the running the episode, like, and how to evaluate the policy? Let's say we play this frozen game 100 times and take the average total reward of it. And that average, because one may be just idiosyncratically bad choice given the initial condition. So can we try it over and over again and take the average? So which policy on average, for policy, how much on average it gets? So this is what we do. The random policy is just getting 16 4 different choices of numbers. So that's a random policy. So the main function is, and I'm going to time it, I'm going to have 2,000 policies, okay? And have this random policy. Let's see how that works out. Okay, so if I just play it randomly, I just pick randomly out of the how many 4 billion choices of actions and just play this game long enough. How much will I get? Okay. And I don't know how long it will take for the random policy. Let's see. So let's come back when it's done. Okay, it's done running. It took 30 seconds. The success rate of 5%. You reach the goal only 5% of the time. So out of the 4 billion choices, many of them are terrible choices that will never reach from the start to the goal. And you only reach the goal by randomly just guessing these 16-digit numbers. It's only 5% of the time reach the goal. I think we can do better, isn't it? So let's see how the genetic algorithm works. So again, libraries and environment, and run the episode. Pretty much similar. So now we have a genetic algorithm. We evaluate the policies. So we run it 100 times and take the average. For each policy, we just run it 100 times and get the average score. Okay. Initially, we have to generate random policies to start with. The crossover is you have the 2 sets of 16-digit numbers, and then with 50% chance of flip a dial, and the random number is larger than 0.5, then copy that cell of policy 2 to policy 1. Here. And that the new policy will be your offspring. So this is something like we are doing this, isn't it? Every digit we go through the policy 1, flip a coin, and sometimes we switch it with the policy 2. This is what we are doing. Okay. So this is a crossover. Mutation is that for each tile we go through, and with a very small probability, 5%, we may switch the tile action choices and create a null policy. So this is mutation. So now we are running the genetic algorithm. So we have initially 200 policies. So we create randomly 200 policies, okay? And we'll go through 50 offsprings, 50 generations of offspring. So we'll create policy population of 200 policies. We get random policies. This is the policy population. Evaluate each policy and get a score for each, and then rank them and get an elite set of the policy ranks of the top 5 one, let's say. Okay, and select according to the probabilities, the policy scores. The higher ones are more likely to be chosen, let's say. Okay. And select the ones here. And if it's out of bounds, of course, you only want to reach it between 0 and 1, so the probability doesn't go over 1. The child set is like the policy 1 and policy 2. We pick one of the policies here from the elite set and another policy from their set. And you do a crossover for them to get a child set. And of that child set, you do a mutation with 5% probability and get a mutated list. And from this crossover to mutated child list, you get an elite set, okay? And keep playing this game, isn't it? And eventually you can get the best policy out of the population. So if you keep running each generation, and we'll run for 50 generations, let's see how well that does. Okay? So eventually it will get us some kind of, so initial generation average score 0. It never reached the goal by picking the random numbers, isn't it? So it's kind of doing terribly. Even in the 4th generation with the crossover and mutation, it doesn't work. We hope that the mutation and crossover will at some point get a combination that will reach the goal, and that will be picked in an elite set. And you can see how quickly it from 0 to 0.5% to gets quickly to 70%, 80%, isn't it? So you can see that the genetic algorithm, once it hits a magic combination of a DNA, the polyseed that actually makes it, it has a way to amplify that offspring to get it. So eventually we are consistently getting somewhere in the 80% range. 80% of the time we reach the goal, isn't it? Average score of 84%, time taken 60. So 1 minute it took for us to get. So this is how to do genetic algorithm using the crossover and mutation and selecting the survival of the fittest idea. Thank you for watching this episode.